We're going to be going over some Newton's second law for rotational motion. So there's a couple of just little things that we want to remember with rotational motion. The first is that the direction matters. And now we're not talking about left, right, up, down. If we're talking about things that are rotating, we're talking about things that are going counterclockwise. We call this CCW for counterclockwise. That is the positive direction. So anything that is going counterclockwise is positive. Now, opposite of that, if we have going clockwise, or there's a force or a torque that's trying to make something rotate clockwise, then we say that is the negative direction. So a torque that is going clockwise is a negative torque. A torque that's going counterclockwise is a positive torque. Okay? So that's some directional stuff. The other thing that we want to remember is Newton's second law. So Newton's second law for linear motion. Remember we said that F equals ma. The net force is equal to the mass times the acceleration. But more commonly we see this rearranged a little bit to talk about the acceleration. And the acceleration is the net force over the mass right there. Well, in a similar light, we're going to talk about Newton's second law for rotation. And using Newton's second law for rotation, remember we have torque. Instead of forces making things accelerate linearly, we have torques making things accelerate rotationally. So net torque is equal to, now we don't have mass because remember with rotation, it depends where the mass is. And we call that rotational inertia. So we have a capital I for rotational inertia. And then the acceleration, little fishy, alpha. Right? And if I rearrange this just like we did before, I have acceleration is equal to the net torque over the moment of inertia. Okay, so that right there is going to be the little bit, the formula we use to kind of structure our thought process behind some of these problems today. Okay, so let's take a look at some of these problems. Let's go here. All right, apparently I need to, don't mind that. Get that out of there. There. Here we have Steven. Steven applies a force F to a disc halfway between its axle. Remember the axle is the thing that it rotates around, so it's axis of rotation, and its outer edge at r/2, 1/2 the radius. The disc can rotate without friction about its center. How should Steven change the location of the force to increase the magnitude of angular acceleration? So a couple things going on right here. Angular acceleration tells me, let me make sure I got the right, there we go. All right, I'm going to be using net torque over moment of inertia. Now, no matter what, this is the same object the entire time. So the moment of inertia is constant. Okay? So this bottom doesn't end up affecting anything. So we really need to worry about the top. Now the top has to do with the net torque. And we talked about last week the torque has to do with how far is there a force being applied, a perpendicular force. Okay, so those two things. If I wanted to increase the torque so that I could increase the angular acceleration, I could do two things. I could increase the radius, like the distance that that force is being applied, or I could actually just increase the force, right? But in this problem, it says, how should Steve change the location, right? So I can't change the magnitude of the force. I can only change where it's at. So if I want the torque to get bigger, I need to change the radius. I need to make the radius bigger so that that gets bigger. Okay, so I'm going to go and see which one of these would be that. Steven should apply the force closer. Absolutely not. Apply the force on the other side of the axle. That would just change clockwise and counterclockwise, so no. Stephen can't change the angular acceleration. That is incorrect. He should apply it at a distance r, which would be further away from the axis of rotation. So D for this one. All right. This same thought process is going to happen a lot throughout these, even though a lot of these problems look different. So looking at this next one, we have a solid beam can rotate without friction around its center 0 when forces are applied. So this little green dot is its axis of rotation. Okay, that would be like this meter stick is a beam. Its axis of rotation is in the middle, and it's rotating like that. Okay. So same stuff as before. We want to know which one of these would give the greatest angular acceleration. So I'm going to think about Newton's second law, and I know that angular acceleration has to do with the net torque and the rotational inertia right there, capital I. Well, all of these beams are the same. So just like in the last one, that means the rotational inertia is not going to change. If the object isn't changing, the rotational inertia isn't going to change. So that has nothing to do with it. So only the torque has something to do with it. Remember, net torque means you add up all the torques involved. So whichever has the biggest net torque is going to have the biggest acceleration, angular acceleration. All right? So let's just add these up. This would be net torque. All right? This would be 2F is the force, and it's getting applied, let's just call this 1 tick mark away right there, right? And that's going counterclockwise, so that's positive. Okay, so this would be positive 1 times 2F. I'm saying that's 1 tick mark away. So 1 times 2F, so 2F. Plus, this is also making this rotate counterclockwise. So this is also a positive torque. And this is also 2F times a distance of 1 from the axis of rotation. So 2F times 1, 2F. So the net torque here is 4F. Okay? We can do that for all of these and see which one ends up with the biggest torque, right? For B, this would be 2F times now 2 tick marks away. And this is making it go counterclockwise, so this is a positive. So this is 2 times the force of 2F plus, and this one is making it go clockwise. So this is a negative torque. So this is also 2 tick marks away. So 2 times negative 2F, because that is a negative torque. It's making it go clockwise. And those would cancel each other out. So this is a net torque of 0. It's definitely not B. All right, let's see here. I thought that was the same as A for a second, but it's not. Each of these is 2 tick marks away. And these are both making it go counterclockwise. So these are both positive torques, right? So when I do a net torque, that's 2 times 2F plus positive 2 times 2F again. So this would be a net torque of 8F, and that would give me probably what's going to be my biggest one, but let's see. This net torque would be the force F is a distance of 1 away from our axis of rotation. So that would be 1 times F plus, this is now 2 away, 2 times the force of 2F. All right, so that's 1F plus 4F. So my biggest net torque would end up being C right here. So C is going to give me the greatest angular acceleration. Okay. All right. Same idea, but now we have Catherine applies a force F to a teeter-totter between its pivot point and its outer edge. at 3r over 4, so 3/4 the radius. The teeter-totter can rotate without friction. So right here is its axis of rotation. Right? Teeter-totter, seesaw, whatever you want to call it. How should Catherine change the location? So it's specifically asking about location of the force to decrease the magnitude of angular acceleration. So when I look at what Newton's second law is, right, this teeter-totter is not changing shape, type of teeter-totter, or anything like that. So just like before, the rotational inertia is not going to affect this at all because the object is not changing. So we can ignore the angular or the rotational inertia. And so this now has to do with the net torque, right? Which torque has to do with radius and force. And this is asking, what should she do to change the location of the force to decrease? So it's not asking what would you do to the force. So the actual magnitude of the force isn't going to be a part of this problem. It's only going to say, how can we decrease the torque? Well, torque is proportional to the distance, right? It's affected by the distance that the mass is. And so if I decrease the distance the mass is, then I can decrease the torque. So I need to find an answer choice that's going to decrease the distance of this force F. So not A, not B. If I applied the force at distance R, 1r would be bigger than 3/4 r. So that would actually increase the torque. So it's not C. So D. She should apply it closer to the axle, to the axis of rotation. Cool. I want to do one more similar to the other one, but on this one we're looking at now the axis of rotation is at the edge. Okay. So which of these is going to cause the greatest angular acceleration? Do a quick check. All of my objects are the exact same. So I know that tells me moment of inertia is not going to affect this problem. So I need to know which one of these has the biggest net torque. So this is 1, 2, 3, and 4. So this would be 3F, right? Distance of 3 times force F. 3F plus 4F. Give me 7F. This one is going to be 0 because this is a negative torque because it's making it go clockwise. This is a positive torque because it's making it go counterclockwise. So these are canceling each other out. I would have negative 4F from this top one and then plus 4F from that bottom one. So they cancel each other out. Over here, I would have a distance of 1 times F plus a distance of 2 times F. So this would give me a total of 3F for torque, right? And then the last one, notice, here I have a distance of 1, 2 distance, right? This is making it go clockwise, so this is negative. So I would have negative 2 times a force F, okay? Now this one going counterclockwise, this is a distance of 2, but it's 2F, so this is plus 2 times 2F. So this would give me a net torque of 4F minus 2, so positive 2F. So my biggest one, my biggest net torque is going to be my greatest angular acceleration. So looks like A. A has a net torque of 7F. So A is going to be my greatest torque, which means similarly my greatest angular acceleration. All right? So hopefully these things help. And if you guys have any questions, hit me up, leave them in the comments, talk to me in class, do what you got to do, and I will see you guys in class.